Hey friends, welcome to the YouTube channel All About Electronics. In this video, we will learn about the Schottky diode. So this Schottky diode is quite similar to the normal diode, but it is different in many aspects. So first, if we talk about the circuit symbol, then this is the circuit symbol of the Schottky diode. Apart from that, this Schottky diode has a low forward voltage drop. Now typically if you see any silicon rectifier diode, then the voltage drop of that diode used to be in the range of 0.6 to 0.7 volt. But for the Schottky diode, this voltage drop used to be in the range of 0.3 to 0.5 volt. And it is also evident from the VI characteristic of this Schottky diode. So here, the VI characteristic of the Schottky diode and the PN junction diode has been shown. And as you can see, the threshold voltage or the forward voltage drop of the Schottky diode is less than this PN junction diode. And this low voltage drop has advantages in many applications, particularly in the high power applications. So let's say we have one rectifier diode and one Schottky diode, and the forward voltage drop of these two diodes are 0.6 volt and 0.3 volt respectively. And let's say the current which is flowing through these two diodes are 50 ampere. So in case of the rectifier diode, the total power which is getting dissipated across a diode will be equal to 50 ampere times 0.6 volt, that is equal to 30 watt. On the other end, if we see the Schottky diode, then the total power which is getting dissipated is equal to 50 ampere times 0.3 volt, that is equal to 15 watt. So for the same current rating, the Schottky diode dissipates a less power and hence it generates the less heat. So these Schottky diodes are quite useful in the high power applications, particularly where the good efficiency is required. Then the next difference is that the reverse recovery time of the Schottky diode is very low. Now if you are not familiar with this reverse recovery time, then don't worry, we will discuss it at the end of the video. But in short, it defines how fast the diode is able to respond to the switching. So basically it is related to the switching speed of the diode. And because of the high switching speeds, the Schottky diodes are used in the fast switching applications, because in such applications the normal diode won't work. So let's understand this point. So at low frequency, let's say at 50 Hz, we are using this rectifier circuit, and in this rectifier circuit we are using the normal diode. So if we see the output waveform, then the output waveform will look like this. That means this diode will allow only the positive half cycle and it will reject the other half. But now suppose if we increase the frequency, and let's say if we operate the circuit at 50 kHz, then we should get this kind of waveform. But actually if you see, this diode won't be able to suppress the negative half cycle, and rather during the negative half cycle we will get this kind of waveform, because the reverse recovery time of the rectifier diode is large. And due to that, it will also conduct for some time in the negative half cycle. So that is why this rectifier diode will not work at the high frequencies. But in case of a Schottky diode, due to its fast reverse recovery time, it is also able to rectify the high frequency signal. And that is why the Schottky diodes are used in the fast switching applications. For example, they are used in the SMPS, where the switching frequencies used to be in the range of 10 to hundreds of kilohertz, and they are also used in the communication applications, for example in the RF mixing or in the detector circuits. So due to the fast switching speed and the low forward voltage drop, the Schottky diodes are used in the many applications. But these diodes also have some limitations. The first limitation is that the reverse leakage current of the Schottky diode is higher compared to the normal diodes, and it is also evident from the VI characteristic of this Schottky diode. So as you can see, for the Schottky diode in the reverse direction, the leakage current is higher than the normal diode. Apart from that, the breakdown voltage of the Schottky diode is also less compared to the PN junction diodes. Or in other words, we can say that the peak inverse voltage of the Schottky diode is also less compared to the normal diodes. And apart from that, the operating temperature range of the Schottky diode is also less. So these are the few limitations of the Schottky diode. But in your application, if you are not concerned over these limitations, then this diode is very useful in the switching as well as in the high power applications. Now that is being said, let us briefly see the construction of this diode. Now in terms of the construction, it is quite different from the PN junction diode. And here, unlike the PN junction, now the metal and the semiconductor junction is formed. So in the Schottky diode, the semiconductor used to be a N-type semiconductor, and for the metal, the different host metals like chrome, platinum and tungstens are used. So here in both materials, the electron is the majority carrier, and when these two metals are joined, then the electrons from the N-type material will flow into the metal, and that will establishes a heavy flow of electron into the metal. Now since the injected electrons have a very high energy compared to the metal electrons, so these carriers are known as the hot carrier, and that is why the Schottky diode is also known as the hot carrier diode. Now once the electrons in this N-type material enters this metal, then still they will remain the majority carriers. So the Schottky diode is unique in the sense that the flow of current is only due to the majority carriers, or in other words, it is a unipolar device. So now, due to the flow of electrons into the metal, the region near the junction on the N side will get depleted of the electrons, and due to that, the depletion region is formed near the junction. And the addition of charge carriers into this metal will form a negative wall near the boundary. And due to that, the surface barrier is created between the two materials, and due to this barrier, the further flow of electron will be restricted. Now, whenever we apply the forward bias, then the strength of the negative barrier will reduce, because now the electrons will get attracted towards the positive terminal. And once again, now the electrons in the N side will be able to enter into the metal. So in this way, the flow of electron is established in the given circuit. And as I said earlier, the barrier potential for the Schottky diode is less than the PN junction diode. So by applying the small voltage also, we can get the desired current. So now let's understand why the Schottky diode has a fast reverse recovery time. And to understand that, first of all, we need to understand what is reverse recovery time. So let's say we have one PN junction diode, and initially it is forward bias. So now due to the forward bias, the electrons will enter into the P side region, and the holes on the P side region will enter into the N side region. But here, to understand this phenomena, let us only concentrate on the one type of charge carriers. So let's say due to the forward bias, the electrons will enter into the P side region, and once they enter into the P side region, then they will become the minority charge carriers. But due to the applied biasing voltage, they will continue to move deep into this P side region. Now let's say suddenly at time t1, the applied voltage has been reversed. So in this case, now this PN junction diode should become reverse bias, and we should not get any flow of current through this PN junction diode. So ideally, this current IF should become 0 after this time t1. But actually if you see, we will still get some finite current after this time t1. So let's understand the reason behind it. So now whenever we reverse the polarity of the voltage, then this terminal of the supply will become negative, and this terminal will become positive. So the electrons which has entered the p-type region during the forward bias will now act as a minority charge carriers, and due to the reverse bias, now they will start moving toward the positive terminal. So due to the movement of these large minority carriers, we will get a flow of current in the reverse direction, and this current will flow for the finite amount of time. So this time is known as the storage time, and it defines the time which is required by the minority carriers to return to the majority carrier state. That means it is the time which is required by these electrons to once again move back into the N-side region. And once the storage time is passed, then the current will start reducing. That means once this electron enters into this N-type region, then the current will start reducing, and eventually it will become 0. So this time is known as the transition time, and the summation of the storage and the transition time is known as the reverse recovery time. So due to this reverse recovery time, the current through the diode will not become 0 instantaneously. But in case of a Schottky diode, there is a no minority charge carriers. So we can say that the storage time for the Schottky diode is negligible, and due to that the reverse recovery time for the Schottky diode is very low, and that is why they can be operated at the high frequencies. So this is the reason why the Schottky diodes are preferred in the fast switching applications. So I hope in this video you understood what is Schottky diode and how it can be used in the different applications. So if you have any question or suggestion, do let me know here in the comment section below. If you like this video, hit the like button and subscribe to the channel for more such videos.